Greetings once again. My name is Philemon Zille from the University of Pretoria. We will commence with the second technical session titled Space for Transformation, Public Value and Development Impact. So I'll be a moderator for this session. We have 5 presenters who are lined up to give us interesting talks. And each presenter is expected to speak for 10 minutes. So please try to stick to the allocated time as much as you can. Then if I see you going over, then you will see me standing next to you and know that you're in trouble. And then after you have presented, after each of you have presented, you'll have a seat, and that will be followed by a round of questions from the floor. Let me call on the first speaker, Yonwaba Adiosi, who will give us a talk on reflectance models for scalable soil moisture mapping using Sentinel-2 data.
Good morning, colleagues. I am Yonwaba Adiosi, as I'm just introduced by Dr. Tsele. Colleagues, if I could tell you that being here now, seated for this youth session, is the best decision you've took in 2025, what would you say? I am very honored to be here, to be part of the youth that is going to be sharing ideas today. We are not only going to share ideas, but we are going to shape the future. Because this session is where creativity meets passion and innovation has no bounds. Ladies and gentlemen, I am going to present to you a soil reflectance model that can predict soil moisture across space and time. This work is under the supervision of Prof. Moses Shaw. Sorry, Prof. I'm still learning to pronounce your surname. Prof. Abel Ramuelo and Dr. Nobuhle Machozi. Just a brief bio. I am working for the CSIR Precision Agriculture Group, and I am my focus is in remote sensing of soils. We're developing innovative techniques for precision agriculture. Just a background on my academic background, I did geology and applied remote sensing and GIS in the University of Fort Hare. I'm happy to see colleagues here that I seated from the first year. Moving to the business of today, to respect time, I will briefly take you through to the synopsis of the work, where we're coming from. We started with sensitivity analysis, where we looked at subtle changes that are responsive of soil moisture. We conducted a canonical analysis, that is a multivariate statistics measure that helps you identify the most influential properties of soil that are associated with soil moisture retrieval. Through this work, we got very interesting results where we pinpoint the amount, the moment that the sensor can be triggered to sense soil moisture. And through this work, it triggered my interest to know while the entire spectrum is affected by soil moisture, beyond that, there is something that is also affecting the spectrum, which is soil clay content. We developed a hyperspectral-based soil reflectance model that considered the interactions between soil moisture content, soil clay content, and their contribution to form a soil spectral reflectance. So this is our model. This is our model where the reflectance of soil is a function of soil moisture content, soil clay content, and the interaction between the two. So we drew the coefficients from a Gaussian distribution, while for the soil moisture content and soil clay content, it was uniform distribution. We tested the model on independent data set from the Eastern Cape. We also tested it from Limpopo province, and to operationalize the model, we resampled it to Sentinel-2 using spectral response function of that platform. Coming to today's presentation, we wanted to ascertain whether this model can be used in Sentinel-2 to predict soil moisture in space and time. These are our study areas where we collected soil samples to calibrate the model. As you can see here, these are the sites where we tested the model. You can already appreciate the variety of soils in color just by looking by your eye, that this is the soils that we chose out of the existing database of soils. We chose them based on percentile distribution of clay content, since we already knew that clay content, accounting for clay content in reflectance modeling will improve the retrieval of soil moisture. Coming to the problem, we all know that soil is important. If soil was not important, you'd be sitting there hungry because you wouldn't have that breakfast that you had this morning. Because soil is the one that is the medium between the crop and the growth. So accurate and timely and transferable soil moisture retrieval remains a challenge in precision agriculture, drought monitoring, and hydrological modeling. Traditional methods provide us with reliable point-based information. However, they are labor-intensive, spatially constrained, and impractical for large-scale monitoring. Remote sensing offers scalable alternatives, yet retrieving soil moisture from the satellite data remains a challenge. Hyperspectral remote sensing, with its narrow bands and contiguous bands, provides promising avenues to predict soil moisture. However, there are also limitation is operational use due to scarce high-resolution open access data. Multispectral remote sensing, on the other hand, is freely available. It covers global coverage, high temporal resolution, and the problem with hyperspectral remote sensing is broader bands. As much as we want to make things operational, the problem that we are facing is broader bands, and they reduce the precision in capturing subtle changes in soil moisture and the complex dynamics in soil. You will appreciate how we started. As we started in the lab at the CSIR, they let me swim in the dark room and to really understand the behavior of soil spectra. This is where I was doing the lab work. And the model that we predicted, the hyperspectral model that we predicted, this is spectra that is generated from the Monte Carlo simulation that accounted for the uncertainties and the complex relationships between soil properties. Now you can imagine moving from hyperspectral to multispectral, from 2,101 bands of hyperspectral spectra to only 12 bands of Sentinel. You can think of how much information you can lose. So we predicted soil moisture using spectral matching techniques that we're just taking Sentinel-2 spectra and we match it to our lookup table that consisted of those spectra, 100,000 of those spectra, soil moisture content corresponding to them, soil clay content, and the interaction effect. So we got these results. You can sit there looking at that R squared and think, these are poor results or these are moderate results. However, if you can appreciate these terms that were included in that multivariate model, you will look at the statistical significance they contributed. Should we have just used soil moisture as the predictor and not account for soil clay content and the interaction effect? Think about what would happen with this only 12 bands of Sentinel-2. That challenge needed a little bit of innovation. So we did spectral engineering, we did feature engineering that included looking at developing band ratios and new soil moisture indices. As the existing soil moisture indices are only looking at the relationship between soil and soil moisture content to predict soil moisture. Our innovation comes with training our machine learning models with a lookup table that incorporates implicitly clay content and the interaction effect. So with doing this, we enable transferable, interpretable, and operational pathway for soil moisture monitoring. So the best model among our models that we trained with this robust synthetic data set was applied to Sentinel-2 to map soil moisture content spatially and temporally. Colleagues, I'm saying spatially and temporally because the lookup table was calibrated with Gauteng soils, as I showed before, and we were able to test it with Eastern Cape's Sentinel-2 data and corresponding measured soil moisture content, and Limpopo. In different seasons, the calibration data set was in 2019, 2020, and 2021. And the calibration, the testing data set for the Eastern Cape was in 2024, 2025 growing season, and for Limpopo, 2025, 2026 growing season. So when we tested with hyperspectral data, this is the results that we got. As you can see, that random forest came out as well performing across other models. And these are the results for the Eastern Cape and Limpopo. And this is just to show you the soil moisture maps across different regions in our country. In conclusion, accounting for clay content and its interaction with soil moisture content in soil reflectance modeling improves soil moisture prediction accuracy. Our multivariate model that explicitly include the soil moisture, the soil clay content, and their interactions, it predicts soil moisture across space and time. The framework bridges hyperspectral richness and multispectral practicality, offering a scalable solution for precision agriculture, water resource management, and environmental monitoring. The current work is focusing on incorporating vegetation parameters for a fully integrated soil canopy moisture mapping. Thank you.
Thank you, Yonwaba, for the interesting talk. Yes, indeed, soil is important, and it's a source of our agricultural produce. So we'll move on to the next speaker, Ms. Anela Mkwekwana, sorry. Yeah, the floor is yours.
Greetings to you all. My name is Anela Mkwekwana. I'm a master's candidate at the University of KwaZulu-Natal. Today, I'll be presenting an ongoing master's paper, which is based on the use of Sentinel-2 combined with SAR remotely sensed data in assessing and in assessing and quantifying soil moisture content for optimization of maize crop in commercial farming systems. This project wouldn't be possible without my supervisors, which is Professor Onisimo Mtanga, Dr. Charlie Matongera from UKZN, and Dr. Kiara Blau from CSIR. So, an increase in population growth and food insecurity has amplified the importance of farming systems, particularly in developing countries such as South Africa. Farming systems are categorized in different types, which include commercial farming systems that are important in achieving national food security. Commercial farming systems operate at large scale. They are key in ensuring food availability. Also, they support local communities offering a wide range of crops, including maize. Maize is regarded as staple food for many countries. Also, it is primarily grown under rain-fed conditions with limited resources. Maize is also regarded as a strategic commodity for food and poverty reduction. Soil moisture availability is a major influencer, is a major factor that influences maize growth. So proper monitoring of soil moisture is important in the development of maize and the final yield. Therefore, there is a need in monitoring soil moisture. There have been various traditional methods that have been used, but as Yonwaba said, these are labor-intensive and they are time-consuming. Therefore, in recent years, remote sensing has been used in monitoring soil moisture because it provides data in a large scale. Satellite remote sensing has been used recently, including Sentinel-1 and Sentinel-2. Sentinel-2 provides spectral data in which they have different bands that can be used to show different characteristics of crops. The aim of the study is to evaluate the potential of Sentinel-1 and Sentinel-2 in estimating soil moisture in maize farms. Their objectives include to investigate the synergic potential of Sentinel-1 and Sentinel-2, combining vegetation indices and backscatter coefficients to improve soil moisture estimation. It also includes analysis of soil moisture variability across growth stages and their impacts on maize health indicators. These include leaf area index and chlorophyll. Also, it was to develop and validate a deep neural network model to predict soil moisture using satellite predictors and field-based measurements. We use different materials and methods in the study. These include data acquisition. It was Sentinel-1 and Sentinel-2, and then field data. With Sentinel-1, We did thermal noise calibration and geometry correction to remove distortions in the image. Also, we converted the linear decimals to decibels for further enhancement of the image. Sorry. And then with Sentinel-2, we did a resampling so that we can match the spatial resolution of Sentinel-2 with spatial resolution of Sentinel-1. And then with the in-situ data, we collected 100 points across the commercial farm in Bronkhorstspruit. And then we got the values for the backscatter coefficient for Sentinel-1, and then for Sentinel-2, we were able to derive vegetation and soil moisture indices. And then we used a nearest neighbor diffusion integration technique to integrate Sentinel-1 and Sentinel-2 images. And we chose this because it does not change the spectral data of the original image. And then the in-situ data was used to calibrate the model at the same time to validate the model. And that's how we got the optimum soil moisture maps. These are the results that we got from the models, and I included the results from the V8 and R2 stage, which was at 35 days and 100 days. And this was the optimal model performance. As you can see in the diagram, is that Sentinel-2 cannot just be used as a standalone satellite. When it is fused with Sentinel-1, V8, and VV, the accuracy increases. It increased from 0.45 to 0.52 with VV, and then 0.56 with VH. And then at R2, it increased from 0.57 to 0.62, and then 0.67. And this is the spatial distribution of the predicted soil moisture across the physiological stages. And this was V3, V8, R2, and R5. And these results indicate an increase in soil moisture in V8 and R2, whereas there was a decrease in V3 and R5. The pattern aligns with this prediction accuracy, which is on this diagram. And then our other objective was to analyze how soil moisture variability impacts maize health indicators, and these include leaf area index and chlorophyll. We can see that an increase in soil moisture also increases chlorophyll and leaf area index in all the phenological stages. From this, the results show that these results show that the comparison of Sentinel-2 cannot be used. Sentinel-2 cannot just be used as a standalone satellite. It needs to be integrated with Sentinel-2 to improve the accuracy, because the accuracy increased in all the prediction accuracies. The findings can also be attributed to the fact that Sentinel-1 star data provides valuable backscattering data that is sensitive to vegetation characteristics. And then all variations in soil moisture were constantly linked to corresponding increases or decreases in soil moisture in chlorophyll. And then based on the prediction of the model, the RMS square was less than 10% in R2 and R5 stages. From this study, we can conclude that V8 and R2 stages are the optimal stages for soil moisture assessment prediction, because these are the stages where vegetation reflectance is at its peak. The backscatter coefficient, VV and VH, improve prediction accuracy for soil moisture assessment. And then the variability in soil moisture influences leaf area index and chlorophyll. These findings of this study provide valuable insights in advancing precision agriculture, particularly in commercial farming systems. And these findings fill a gap in existing studies by applying smart agriculture approaches to the global south for improved maize crop production. Thank you.
Thank you, Anela. Yeah, no, interesting presentation. And as I was looking at your slides and also taking note of what the previous presenter talked about, it underscores the fact that accurate retrieval of soil moisture is a critical parameter for precision farming. So now we'll move on to the next presenter, who's Snetemba Ndlovu, who's a doctoral candidate from UKZN, and will give us a talk on modeling soil organic carbon in woody encroached grasslands.
Okay. Good morning, ladies and gentlemen. My name is Usnet Hembandlovu, and it's a pleasure today that I'm able to share with you some work that we have done in collaboration with the University of KwaZulu-Natal, the Water Research Commission, as well as the Center for Transformative Research and Food Systems. So my title of the presentation today is on looking at multi-temporal analysis of crop water status when we looking at the neglected and underutilized taro crop and using high-resolution thermal and multispectral data to perform these analyses. So just to set the stage for discussion, as we know that climate change is a global environmental threat that has adverse effects on agriculture crop production. And this is especially the case in developing regions that already have challenges, pre-existing challenges of hunger and food insecurity. And we see that this is more profound now in smallholder farming systems who often rely on natural irrigation, who do not have the resources. Therefore, they are more vulnerable to the impacts of climate change. And we see that unlike commercial farmers, smallholder farmers don't have those resources to sort of plan and sort of bounce back when it comes to extreme weather events. So this does call for a paradigm shift where we could transform our existing agriculture systems to incorporate crop species that build resilience and strengthen the adaptive capacity of our smallholder farming systems against climate change. So a promising approach for addressing some of these challenges is through the use of neglected and underutilized crops, right? So for instance, if we look at taro, also known as amadumbe, this crop has been identified as a future smart crop because of its ability to be drought and heat tolerant, as well as having the ability to withstand even adverse conditions, right? And additionally to that, we see that this crop has a high nutritional profile. There's also studies that show that it's a source of natural steroids. So if we could sort of demonstrate the potential of integrating taro as a climate resilient crop, and for us to promote nutrient-sensitive agriculture, it will then be valuable for ensuring food security. However, we see that the spatial and empirical research when it comes to its water status is currently anecdotal and there's limited available knowledge on that. So while it is drought stress, it is not immune from stress completely. As well, when it comes to the tuber quality of the crop, the moisture content does infer into the texture and the palatability. So it's important that we could monitor this crop, the water status of it spatially as well as temporally. And then how do we go about doing this? So studies have shown that when crops are under severe or some sort of water stress, they exhibit different physiological changes that take place. So when a crop is under water stress, we see that the stomata would close and then increases in temperature, the crop temperature, because of evaporative cooling. So if we could go ahead and then quantify these changes across the different growing season, looking at the stomata conductance, the soil moisture, chlorophyll content, we could then be able to see exactly the status of these crops on a continuous basis. And as my colleagues have mentioned, and over the recent days, we've been hearing how unmanned aerial vehicles, also known as drones, present even in the exhibitions, poster exhibitions outside, that they have presented a new and a promising solution for us to get high resolution spatial imagery, even at the resolution of centimeters, right? So allowing us to get accurate, precise information of the crop water status even at the field level. So this then promoted or prompted the study where we sought to then evaluate the utility of multimodal thermal as well as multispectral remote sensing in assessing and monitoring the crop water status of taro within smallholder farming systems across multiple growth stages. So this study was conducted in Swaimane, which is located in KwaZulu-Natal, not far from Pietermaritzburg. And we see that the environment where the study was conducted is a good example of an organic farming system because these areas rely predominantly on natural manual labor methods, traditional methods, natural rainfall for irrigation. And we see that climate projections in this area have stated that there would be increases in temperatures as well as unpredictable rainfall. So it's been identified by the Mgeni Resilience Project as an area that is vulnerable to the impacts of climate change. So when it came to the data collection, we utilized a twofold approach whereby we went in to collect the in-situ measurements, right? And for this particular paper, we focused on the stomatoconductance and leaf temperatures as the proxies of water status, but we did go ahead and collect additional measurements of soil moisture, chlorophyll content to complement our data set. And as you can see, this was us collecting these measurements in field and going through the lab processes of quantifying these attributes. Additionally, we also utilized the DJI Matrice 300 drone, which was mounted with a MicroSense Ultim sensor, which covers the blue, green, red, near-infrared, and thermal bands of the electromagnetic spectrum, and we were able to obtain imagery at a 9.6 centimeter resolution, which allowed us to see precisely what was going on with our crops. We then went on to integrate these data sets with our high-resolution imagery as well as our in-situ measurements, and we used this to calibrate a model, a deep neural network model, whereby we were then able to compute or develop these optimal crop moisture maps. So, what we did notice when we are conducting this study was a significant presence of non-target elements, right, such as your soil background. And as we know that these introduce noise into the imagery and they obscure the accurate detection of what we are interested in. So we then went on to explore different image segmentation techniques where it allowed us to extract pure canopy pixels of just the crops that we were looking at and remove the soil background interference. And from that, we were then able to predict soil moisture and leaf temperature at the emergence, vegetative, and maturity growth stages. And the vegetative growth stage, of course, produced some of the most optimal models, up to R-squares of 0.96, which is expected because of the optimal physiological state of the crops during this time. And then we ensured that we tried not to just stop at creating these deep neural network models. We wanted the farmer to truly benefit from the project that we are sort of doing. So we ensured that we could create some spatial-temporal variability maps showing the stomatoconductance state as well as the leaf temperature state at each growth stage throughout the season. And then we went on to apply critical threshold measures whereby the crop will now be in a state of water stress. So informed through literature, we were able to identify all the areas where stomatoconductance was less than 50 moles, all the areas where leaf temperature was less than 10 degrees and greater than 35 degrees, which indicated severe crop. As you can see, when it comes to the emergence growth stage, we have the highest number of stress crops going on, right? But what does this mean for the science community? And most importantly, what does it mean for the smallholder farming systems that we work in? We created the maps, and basically this research, the whole idea of the research was to ensure that such community-based research contributes towards improving smallholder farming systems and ensuring local and regional food security in this area. For example, through these maps that we produced, able to see where the crops are severely stressed can be useful in informing the next growing season of where farmers need to target additional sort of management practices, maybe additional irrigation, maybe additional fertilizers to ensure optimal yields at the end. Furthermore, the research did give back to the community by employing the community members as local field workers, where they assisted us with upkeeping of the field and weeding of the field. And what also happened was that it allowed us an opportunity to engage with the youth in the area as well as with the next generation of scientists. So whenever we were out in the field, we always used the opportunity to explain to especially young children who came to join us exactly what we are doing, of course in layman terms, for them to sort of understand this and see the importance of agriculture and science in the future. But ultimately what we envision is to have some sort of digital tool, right? Some sort of digital tool that could integrate machine learning predictive models and high resolution imagery that can be developed for smallholder farming communities such as the one in Swaimani, where it will allow them to have almost near real-time access to the status of their crops. So this is a prospective research that we are working on and we are putting together, and we would like to invite potential stakeholders who would be open to collaborate with us, especially from computer science side, community engagement side. We would love this opportunity to continue this journey with you guys. Thank you very much.
Thank you very much, Snetemba, for the interesting talk. And I like the fact that you did highlight the public value of your findings, particularly for smallholder farmers. That's when you talk about taking EO to the people. So our next speaker is Mr. Sfundo Matinyani, who will present on modeling soil organic carbon in woody encroached grasslands.
Ladies and gentlemen, I greet you all. My name is Sfundo Matinyani, and today it is a pleasure and honor to present my research project, which is titled Modeling Soil Organic Carbon at Multiple Depth in a Woody Encroached Grassland using integrated remotely sensed data. According to literature, it has been proven that most of our grasslands across South Africa, across the world, has been undergoing a significant transformation where we see most of our grasslands being transformed from just being a pristine grassland to a woody dominated ecosystem or landscape. And this has been observed all across Africa and even across the world. And this has a severe impact on the grassland ecosystem because of the crucial role that these ecosystems are playing on the natural environment or even on our lives as humans. So, the dominance of woody plants within a grassland ecosystem, one of the impacts that it has is that it reduces the productive or the landscape that can be used by livestock for grazing. So it reduces the quality of productive grazing landscape for wild herbivores and also for our livestock. It also reduces the frequency and the intensity of grazing and fires. And these are primary engineers when it comes to maintaining a grassland. And also the dominance of woody plants within a grassland, it has a pronounced impact on below ground on nitrogen and carbon pool, which is soil organic carbon. Now, one will ask, why are we worried about soil organic carbon? We are worried about soil organic carbon because of the role that it plays within a landscape or within an ecosystem. One of the benefits of soil organic carbon in grassland is that it provides various ecological services such as regulating climate, improving water quality, and supporting biodiversity. It also improves the soil structure, retain water, provide plants nutrients, which are critical characteristics for maintaining and increasing the resilience of soils towards droughts and floods. So a decline in soil organic carbon can really trigger the loss of soil quality and productive landscape that are critical for our daily lives and the ecosystem. So there is now a knowledge gap when it comes to the influence of woody plants to soil organic carbon. Not that literature is not there which speaks about these two factors, but the interesting thing about this topic is that most of the studies that have been conducted, it shows that there are so many contradictions when it comes to whether wood encroachment increases or decreases soil organic carbon, which is quite interesting to explore and to really try to understand what is the impact of of wood encroachment when it comes to soil organic carbon concentration, especially in wood encroached grassland. And also most of the studies that have been conducted trying to investigate the influence of soil organic carbon, especially in deeper soil layers, have mostly utilized traditional methods. Now, remote sensing give us an opportunity to further interrogate or investigate the influence of wood encroachment within impact of wood encroachment on soil organic carbon at different spatial extent. Therefore, our aim was to estimate soil organic carbon at various depths, which was 30 centimeters, 60 centimeter, and 100 centimeter in a woody encroached grassland by integrating Sentinel-1, Sentinel-2 planetoscopes, satellite imagery, and topographic variables. The reason that we integrated all these data set was because of the limitation. After reading the literature, you can see that there are some limitations that were observed, and then to try and bridge these limitations or these gaps, we then integrated these data sets so that we come up with robust findings. So our study, we coupled random forest model and remote sense data to model the distribution of soil organic carbon at different depths of woody of busy nature reserve affected by woody encroachment. The study also evaluated the spatial distribution of soil organic carbon from a woody encroach to a pristine grassland. So we established a transit which was running from a woody encroach to a pristine grassland. We just wanted to see, as you move along this transit, what happens to the concentration of soil organic carbon. Is it increasing or decreasing as you move from a pristine grassland to a woody encroach grassland? So this was our study site, which was a Beasley Nature Reserve, which is located in Pietermaritzburg, which is just 7 kilometers away from the CBD. Interesting fact about this nature reserve is that it is under significant influence of woody encroachment. However, we still have some patches of, as you can see there, we still have some patches of pristine grassland, but most of the area, is dominated by woody plants. And interesting enough is that this area was once a pristine grassland, but because of poor management, we find that woody plants are now more dominant in the area. So now we want to see what is the influence of these wood intensification on soil organic carbon in this area. So we conducted quite an intense data collection. As you can see from the picture, it was quite intense because we were collecting soil sample from different depth up to 1 meter. So we managed to collect about 360 soil samples, and then those soil samples, they were taken to the lab for analysis. We're using a Lawson ignition method to extract soil organic carbon values. We then acquired different images, which is PlantScope image. We also acquired Sentinel-1 and Sentinel-2 images. And then from these images, we were able to extract different vegetation indices according to the literature that we believe that they are more suitable for our study or for predicting soil organic carbon. This included your NDVI, your GNDVI, your red age, and what's not. We also, using your digital elevation model, we also extracted some topographic variables, which included elevation, expect, slope, and topographic wetness index. And then we took all this data, and then we ran a model which was a random forest model using all these predictor variables to try and predict the distribution of soil organic carbon within our study site. Right, so from our result, you can see there the Bose and Whisker diagram here. It shows that most of our soil organic carbon was concentrated at the depth of centimeter, but as you go down to 60 and to 100 centimeter, it started decreasing. So which means that within a woody encroach grassland, you will find that the more organic carbon is concentrated on topsoil between 0 to 30 centimeters. But as you go down, it tends to decrease, which is quite interesting. Also, the graph from the transit that we established. You can see, so the transit, we separated into, like, we had a woody and a pristine grassland. So this was where we have 0, there's a boundary between the two landscape. And then you can see as you move from the boundary towards the center of a wood encroached grassland, soil organic carbon tends to increase in the center. But as you move away from the center, it tends to decrease again. And same observation when you go towards the pristine grassland. And from our model, the accuracy of our model, this was 0.78. Also, our predictor variables, the one that had a good performance, or that was VH, band 11, slope and VV. So these were the most important variables when we were predicting our soil organic carbon. Right, so this is our map, spatial distribution map, which shows the distribution of soil organic carbon in our area. So the map on the right is it's a classification map which just classifies the area. These are woody encroached areas, and the green ones, those are pristine grassland. So that at least when you look the map on the left, you can really understand which areas are dominated by more of soil organic carbon. So you can see that the areas here, pristine grasslands, you see here we have about like green colors, which shows that there were low values of soil organic carbon. But here, where the areas that is dominated by woody plants, you can see that we had higher concentrations of soil organic carbon. Then what does this mean is that the areas with more woody plants tends to have more of soil organic carbon. But the areas that are dominated by pristine grasses tends to have low values of soil organic carbon. And there are different, there are a number of explanations. The that explain why. Then, for instance, one would question why are we within a woody encroach grassland, why are we having more of soil organic carbon within 30 centimeters? Because we'll assume there are roots and what's not. So when there's decomposition, because when we speak about soil organic carbon, roots, they play a vital role when it comes to the organic matters on the soils. And from literature, it shows that so our study area is less than 100 years. So if the area is less than 100 years, it means that that area is not old enough that the roots can then like decompose, and then we have enough organic matter on the ground. At least it must be more than 100 years or 200 years. Number two, on the study area, we had an issue of the top rock as well. It was just closer to the surface, meaning obviously if you go a bit down, you will find less of soil organic carbon. So soil organic carbon in the study area mainly dependent on leaf litter. So that's why most of the soil organic carbon was mostly concentrated on the top soils. Or yes, so. The study established that the integration of spectral information with vegetation indices provide valuable information for monitoring the distribution of soil organic carbon within the woody encroached grassland. We concluded freely accessible SAR data and PlanetScope data and topographic variable factors provide more opportunity to quantify soil organic carbon stock in grasslands. The study is beneficial to reserve managers or supervisors and policymakers to make informed decisions on conserving the nature reserve. The methodology presented by the study is a cost-effective and time-efficient procedure of monitoring soil organic carbon distribution across a woodly encroached grassland, and the reserve managers can use the insights of the study to establish effective land management patterns to preserve and maintain a soil or organic carbon pool within the nature reserve. Thank you.
Thank you very much, Mr. Sfundo, for the interesting talk. Indeed, it will be interesting to see how your model works when it's transferred across different areas in South Africa, as there are sites where we do have problems of wood encroached grasslands. The next speaker, the last, is Mr. Tamuka, who's a doctoral student from Cape Peninsula, University of Technology, and will be giving us a talk on integrated remote sensing and machine learning for ocean plastic litter detection.
Good afternoon, everyone. It's not easy to be the last speaker, having to know that I'll be detecting what time we'll be going for lunch. All right. My presentation is based on an ongoing doctoral research. So unfortunately, I'll be stingy with some results because of ethical reasons. But the idea of this presentation is to show the audience that it is possible to use Earth observation data to detect ocean plastics. And I am from CPUT, the Cape Peninsula University of Technology, and I want to acknowledge my supervisors, Professor I.E. Davidson, who's the director of FSAT, and then the absentees who are Dr. Babalola and Dr. Conrad Sparks from the Center for Sustainable Oceans. All right, this is my short bio. Due to time, I'll skip it. You can read it when the slides are published, along with the presentation outline. All right, there's been a rapid production of plastics ever since the 20th century. And with more plastics being produced, it means there's more plastic pollution around the world. And one of the worst places where plastic can end up is in the oceans, because that is going to disturb our oceanic life. So this can be through entanglements. So I believe some of you have seen some videos of sea turtles being entangled with fish nets, and they are rendered immobile, and they can't go swim and find food, and they end up passing away. One of my co-supervisors, Dr. Sparks, is leading the Center for Sustainable Oceans at CBUT, and this research is based on microplastics. Which microplastics is plastics are secondary source of microplastics, and then so it has been discovered from fish samples that have been collected in some shores of Cape Town that more than 50% contains plastics. So will give rise to possible human health risks. Maybe we would like to avoid this so that we don't blame seafood lovers for causing another pandemic. So the current detection methods, they lack accuracy and efficiency. So some of these methods to look for plastics in the oceans can be beach litter surveys, and also to deploy some ships in the open sea. Furthermore, there's limited range in which these ships can go out of the sea, and also the frequency at which these campaigns are conducted is quite low. Which brings us to our research aim, which is to use remote sensing. And these days we are throwing AI at everything. So we are also going to integrate a machine learning to improve detection methods. So why remote sensing and machine learning? Well, remote sensing offers large-scale surveillance. So it means those areas which are remote where we can't possibly reach, the satellite can reach those areas. And also satellite offers high-frequency monitoring. For example, some of the Sentinel satellites, they revisit same site approximately after every 5 days. And also, we have high-resolution data options, can be from Sentinel or from Prisma. And when we integrate with machine learning, it of course increases our detection of these plastics. And then here, this is one of my publications where we looked at many remote sensing methods that has been used. This includes multispectral, hyperspectral, synthetic aperture radar, and thermal infrared sensing. And then we also discussed about the pros and cons of each. And one of the discussions was to use intermodal sensing. I believe my colleagues here who were presenting, you can see that they were mixing different satellite sensors from different satellites on board. All right, so this is the general workflow. Not like it's supposed to be like this, but it's flexible, but this is the general workflow. So, in order for us to develop a machine learning model, an efficient one, we need data. And data is very important, not only just satellite data, but also ground truth data. Because if you get data and we don't know what is in that data, it will be difficult to validate what is inside the data. Further, after this step is to perform pre-processing. This is also another important step because this sharpens how your machine learning model is going to perform its duties. So there are a variety of range of pre-processing from atmospheric correction, pan sharpening, cloud masking, sun glint correction, and radiometric calibration. So my paper here also went into detail into more of these pre-processing methods. And not all of these methods are meant for for example, I cannot use pan sharpening on maybe, let's say, just multispectral because pan sharpening is needed for when you have multimodal sensors and you need to do data fusion. After that is feature extraction and selection. So here we will be taking our spectral bands, and also we can add features such as indexes. I believe you've heard enough about indexes because they've been spoken a lot with my colleagues here. So when we are feeding these features into our machine learning model, we need to label them. So in this case, this is where our ground truth data comes into play. Without ground truth data, we will be wasting our time in this case. And then, from the extracted and the feature selected data, we feed it to our the state-of-art machine learning models that are out there. So, when we are training these machine learning models, there's a rule of thumb where we don't use all our data. At least we use 75 or 70% of our data to train and 30% for testing. So, and also, we will use multiple models that has been developed, as I said, and also we will check at metrics. So metrics such as accuracy, precision, recall, and F1 score. And then from that, we'll look at what each model is good at detecting. And then we'll employ ensemble learning so that we take the best of these models to create our own model. So we use spectral analysis to know if there's plastic or not, but it has also been discovered that not only can spectral analysis can detect plastics, it can also detect the type of plastics. In this case, polymers. So it can be PET, HDPE, based on the hydrocarbon bonds. And usually it's to detect those different signatures, we use the shortwave infrared region, which it is very good to isolate different polymer types. And then in general, when you want to detect or see the difference between water and plastics, in general, especially in the near infrared region, water absorbs more light compared to plastic. So those features in that near infrared region can be used to isolate plastics from water. What about plastics from vegetation? Because we don't necessarily need to send our service out just to remove vegetation, because vegetation has no harm to our oceanic life system. So there are already some general indices that can be used to differentiate in between vegetation and plastics. Usually it's in the red or red age region where chlorophyll absorbs most of the radiation. And then there are some references there to verify these facts. And here is an example of one of the literature. In this case, you can see here, in between 700 micrometers, nanometers, and 1,000 nanometers. You can see, according to those labels, the green one is plastics, fishing nets, and then the black one is plastic bags. So you can see in that region there, we can use that region to separate in between plastics and water. Also, in the region after 1,600 nanometers, nanometers. And then another image there. So these are reflectance values that have been taken after pre-processing. So in this case, it was after atmospheric correction. So some of the data were used they used Senko to process, to do atmospheric correction, and then some of the data they used Acolyte. And you can see, even though we are doing, they're doing pre-processing, you can see the peaks are different. So it means there's a possibility that atmospheric correction might remove some important features required for plastic detection. So this is also part of the research to see what are the effects of pre-processing our data. And then, like I said before, I need to be stingy with my data. So this is in an upcoming publication where we have this ground truth data, so you can see there are coordinates there, and then we have access to this data here. So in this case, we wanted to see the effects of atmospheric correction. So it's an ongoing research. So this is L1 data. So this is before any kind of processing, other than processing that has been done from L0 to L1. And then one thing I forgot to mention, you can see these are different polymer types of plastics, and these are picked because these are the most common plastics that are found in the oceans. So in this case, we have HDPE, PET, PS, and a mixture of these. And in this pre-published research, we looked at the features of these plastics. And we're back with spectral indices. So I'm not going to go into detail, but spectral indices are important to add to features that we need to add to our machine learning model. And which is why we would prefer to use hyperspectral, because hyperspectral offers more bands compared to multispectral. So with hyperspectral, we have more features to feed our algorithms. So what are the expected outcomes? So the first one is an improved detection and accuracy of mesoplastics and macroplastics. Although we did not include microplastics, but it will be part of the research because it is quite a new field. So we really need experts to help us detect microplastics, because the smaller the plastic, the more species can consume. And then with integrating remote sensing data with machine learning, it offers enhanced detection of plastics from natural debris. Furthermore, it offers real-time monitoring potential using satellite visits. So in this case, it is possible to predict plastic hotspots over time. And also it can be integrated with GIS maps, so we can integrate or produce plugins that we can add onto our QGISs so that we can be able to efficiently detect plastics. So what is this research is going to contribute to the National Space Dialogue? First of all, it's demonstrating that Earth observation is needed for environmental sustainability, not only in ocean plastics, but also monitoring our crops in our soils, like what some of our colleagues has demonstrated here. And also, this research aims to support marine policy and conservation strategies, especially for marine life, so that we can preserve our seafood. And then this research will offer a framework that is scalable to other African coastlines. So, and also offers potential real-time, it offers potential for real-time cleanup response. In conclusion, integrating remote sensing with machine learning can significantly improve detection and monitoring, and it is also scalable and can be automated for feasible and is feasible for South African coastlines. And this will bridge science, technology, and policy for oceanic health. And there's need for generating data, especially labeled data, for South African studies. So in this case, we have to consult with SANSA if they can offer us some labeled data, specifically ocean plastics, so that we can work with them. But in essence, the best way for remote sensing to be utilized effectively is to combine different remote sensing methods. And you can go on to read my survey paper that I showed you earlier, which details everything there. And maybe some of you professors and researchers can come up with research topics for your prospective students. And this is the literature. These are the references that have been used for all your cross-references.
Thank you, Mr. Tamuka. Yeah, I see you've given us, those who are in the academic space, you've given us a task. So we'll go online and look for papers to develop topics for students. Yeah, and thank you very much for the interesting topic. This was an interesting study, also showing the integration of EO data with machine learning, for the accurate detection of plastics in our oceans. I would also like to thank you presenters, all of you, for keeping the time, right? I just want to mention 1 or 2 points. As I was sitting there, I was also thinking, 2 points that I can, use or mention, to sum up, my observations as you were presenting. So it is clear that, so after this, by the way, I will open the floor for the questions, right? Yeah. So, yeah, I found that all your talks were interesting, and clearly your work demonstrated the importance of EO data for an in-depth understanding and account of terrestrial challenges, including the ocean or coastal waters. The last point is that multi-scale and multi-sensor remote sensing and EO data, coupled with data integration, are at the center of accurate retrieval and mapping of terrestrial and ocean biophysical and biochemical variables. So, yeah, with that, I would like to request the audience to throw some burning questions to our panelists here.
I don't know if that is actually possible from the optical products that you are using, given the fact that the plastics that you are looking at, they are highly dynamic, and the Sentinel data that you are relying on gives you the imagery in 5 days' time. So which means that the plastics in the oceans have already moved to the other area. So I'm not sure how are you planning to sort of like account for that, given the fact that the system that you are trying to monitor is quite dynamic.
Thank you for the question and your interest in my presentation. So it is true that microplastics are quite difficult to monitor, which is why as engineers we need to try to see how we can use the current technology to achieve that. So there has been some surveys that have been done. There's this one guru who in remote sensing in academia is called Shungudze Moyo Garaba. He actually has a spectral library for microplastics. So although they were detected like in close proximity, but it gives us like an idea of what is the behavior of these microplastics under spectral analysis. But currently, we are mainly focusing on meso and macroplastics. Microplastics is a bit of a challenging thing to do, but we are open to suggestion from engineers and experts regarding things. I don't know if this answers your question, or did I answer all your questions?
Because you mentioned that you are looking at the extent of the plastics. So for me, I was not really interested whether you are looking at the microplastics or any type of plastic that you are looking at. I'm trying to see how then you can use the Sentinel product to monitor something that is highly dynamic. For example, the plastics that you are monitoring in the ocean, they move with the current. So if you come in within this hour, you'll find them there. Then in the next hour, you'll find them in another area somewhere else. So I'm trying to see how are you going to actually account for that from the optical data, and also the size of the plastics that you are looking at. I'm not sure if you are really going to detect them from the Sentinel data, given the spatial resolution of the data that you are considering into looking. And because you probably need to have indicators that can be picked up from the 10 meters resolution of the product that you are going to be looking at.
There are different tools, methods used for that detection. For example, in Japan, at TUMSAT, Tokyo Marine University of Science and Technology, they use ocean vessels to go to the perimeter and capture data, which they then process. We also looked at the use of drones across specific areas of interest. The third was use of low-flying aircraft, just a plane to capture information, in real time in a specific area and location. Now, because we are a center of excellence in nanosatellites in Africa, one of the things we are doing now is looking at the potential and the possibility of developing those optical sensors you're talking about right now, where we can use our nanosatellites in low Earth orbit for such detection. That's work under development. So this research is just to give you a snapshot of the bigger picture of what we are doing. And there are a lot of information here that we haven't disclosed just intentionally. But your questions and your comments are valid, but we have answers. Thank you.
Furthermore, to add on to what Prof said, you mentioned about current, like plastics are dynamic, they move. So remote sensing data is possible to change remote sensing data to time series data, and then we can use that information to predict where those plastics can be. Thank you.
So I want to know which classification method did you use to get the spatial distribution map of the woody grassland, and also particularly detecting soil organic carbon? And then to Ms. Anela, I want to know what were the limitations encountered using the deep neural regression model?
I use a supervised classification on Google Earth Engine. Forest.
Okay, so particularly what I wanted to know was that was it a pixel-based or an object-based classification model?
Pixel-based.
Okay, your question is what were the limitations encountered using the deep neural regression model?
It was computationally intensive, so my computer would die sometimes.
Okay. Can we have another pressing question? Oh, some more. See the additional hands here. The gentleman over there. Yeah.
Good evening. Mine is just a compliment to the last presenter. I think this project is very interesting, and I think that's what makes a PhD project. You see, those pending questions, don't take them as a discouragement. I'm wishing you good luck. Thanks.
I saw a hand somewhere there. Oh, there. That side, yeah.
Thank you for the very interesting presentations. And I can't remember, I think it's Anele. I was very impressed by the work that you've done, and especially because it touches on the community side. But my question then is, given the kind of work, and especially you're talking about coming up with an application and all that, and the data sets that you're looking at, those are very expensive data sets. How will this be possible for communities? Because, open data sets cannot do the level of work, or they cannot be as competitive in providing the same results that you got. So I just wanted to find out how will we be able to access data that is able to help with precision agriculture at that level for communities that obviously cannot afford this kind of data.
Thank you very much for that question. I think that is why I ended my presentation with, we are looking for collaborators. We're looking for assistance. We know that the CSIR has done a great job in implementing the PAIS system, and we're hoping to have something similar created. We know that the data sets that we used in our study was drone data set, which is available in near real time. But now we want to explore how we can integrate like Sentinel, satellite-based data sets, maybe your Planet Scope, even some of the data sets that was presented yesterday. I think it was OMEO, I think, the new satellite that's about to launch. So we're definitely wanting to see how can we come together, especially in an environment such as smallholder farming systems with limited resources. Of course, it will take us as the researchers, as the scientists, to come up with this funding to be able to develop such a program to give back to the community members, because we spend a lot of time working in these communities, using their smallholder fields, coming into their spaces. I think it's only fair that we sort of give back to them, and we as a research community can come together and find optimal methods, cost-effective methods of doing this. Thank you for your question.
Thank you. Another hand. Oh, there we go.
I just want to say thank you to the presenters again, like everyone else. We appreciate the work that you're doing. But there's a question to all of you, but I will just start by saying, I represent a company that works with the communities, like taking the technologies that we're talking about here, that most of the companies are providing here, into the communities. So, which means we ended up, like one of the things that we've done is building mission control rooms in rural villages, so that the villages can utilize those facilities to do things like maybe monitor their own floods and then monitor their own disasters. But there's a question I want to ask from you. I know universities may be limited, but what more can be done? What more can private companies do? What more would you like, as university students and researchers, what more would you like governments to do? I think hearing from you and your challenges that you're having ahead, one of your challenges is computing power. So I think maybe if we hear from you, maybe we can expand as a private company some of the offerings that we do, because I was saying to one of the university professors here that we have those control rooms that are now available that can be utilized by research students. But what more would you like to see done?
Mm-hmm.
Thank you so much for that question. It is a very important question. As we sit in those offices and do research, we pinpoint a lot of things, including the bands that are sensitive to various variables. I would like to see the private sector or the government launching a satellite that will directly talk to different specific parameters that we're looking at. For example, we have a drone at the CSIR, but it is up to 1,000 nanometers. But the work that I've done is pinpointing spectral bands that are beyond that point. So this important work that we do, we see statistical significance if it would be appreciated in terms of getting those sensors to really detect these parameters we want to know about, so that we can feed our models so that they can be more accurate. Thank you.
Thank you for your question. I think the private sector can provide funds and create programs like NGOs where they can be able to teach farmers about their farming methods, like new farming methods that they can use, like how they can be able to irrigate their crops regularly to reduce water stress and early detection of droughts or floods. Thank you.
Just to add on what has been said by my colleagues, I think as the private sector, government sector, you guys have access to funding. And I think it's important that we remove the silos, which I think universities often sit in these silos and sort of on the outskirts of what's happening in the current spaces. So if you could try to work together in this. And then I think if you could assist each other in terms of improving the current sort of curriculum or additional resources when it comes to the normal community members, the civilians, and then also school programs whereby we could start teaching students from a young age in terms of what is currently happening in the sector, because we see a great disjoint in terms of what's been taught at school and then what's been implemented in real life. Thank you for that.
Yeah, just to echo what my colleagues have mentioned, we spoke to these community members, and then they said to us, you know the problem, that's why they are so reluctant or hesitant when it comes to us coming to their areas to conduct the study, because what we do as academics, we just go to the area, we get our data, we process the data, we produce our PhDs, and then they never hear from us. So we don't take that knowledge back to the community. And really as my colleagues have been saying, if we can be given that platform, obviously we can't implement, we don't have funds. But if now we are working with government, or even religious leaders within that community, we can be able to share the information, and then some of the things they can be implemented within that specific community. Thank you.
Okay. Basically, everything has been said with my fellow colleagues here, but it all goes down to the memorandum of understanding between the two parties. What we can do is to motivate, but in terms of decision making and drafting that paper, it's out of our hands. That's all I have to say. Thank you.
Thank you, the presenters. Thank you, the audience. Those questions you have raised are important, and certainly they are good food for thought. I think, yeah, the session is adjourned, and what is next now is a lunch.